Okay, we will continue with this little MATLAB program, making it a little bit better. It's not so nice the way I've done it here, but it's a sort of the first version you will try when you have a problem. Quick and dirty. It's very simple and straightforward, straight to the point, and actually, yes, it will work. What is not so nice about it is the following. Here you have a loop with real numbers. That is not so nice. It's not good programming. You should use integer, not real numbers in a loop. So here we now could have done something like this. We have specified the maximum time, and we have specified the time step. How many time steps do we need? Well, that should now be, say, some n max equals, and now we will have maximum time divided by delta t. But they are not integer, they are real numbers. So here we should use round, for instance, making him to the closest integer. Then we know exactly how many time steps that is required to solve it. And instead of using time now, I will use, say, n equals 1 all the way up to n max. This is much better. When you are dealing with real numbers, you might skip or miss one for the latest time step, for instance. Here it's not a big deal, but this is nicer. To be the same program, of course. Second, the way I have programmed the graphics is stupid. Really stupid. And if you have a very big program, I can actually show you. Draw now. Draw now. That's an information to MATLAB. I want the graphics displayed while you are simulating. Normally, if you just have some plot sentence, he calculates first and then he shows all the graphics afterwards. But now he has to provide you with the graphics during simulation. That would be nice. I don't see much. What?
You change the n to n max so it doesn't move, or you don't have the time in the equations.
No, I don't need to. But. Thank you. So here we now need some time. Time equals n times delta t. Thank you. And now you can see he starts out quite fast, and then he goes slower and slower and slower. Because MATLAB is so stupid. He's incredibly stupid. Every time he wants to draw a new circle, he has to draw the entire figure so far. So he sort of accumulates more and more work for himself. So if I continue the timeline here to 100 time units, we could have, continuing here tomorrow or something. So he's extremely slow using the graphics this way. So don't do it unless you really need to. I'll show you later some tricks that you can work around this. It's a nasty problem, so Of course, here you just skip that one, and then he does the simulation and then draws the graphics sort of finished. That's okay. Instead of doing it like this, a better way to do the programming is the following. You do all the calculations first. Then in the end you do all the graphics. Then we have to store our variables somehow. So here now I have my unknowns v and x and also time. So this sentence here we remove, and instead here we have to create storage space for all our unknowns, meaning we have to construct vectors or matrices. So for the v, I use big letters. MATLAB differs between small and big letters. So v number n, that's the velocity, small v. Big X number n equals small x, and finally time number n, that's the small t. So not the smartest way to do it, but it will work. And I mean, for us it's more important to have a good program where you easily can see what's been done, instead of doing it smart, efficient. That's not our job. We are not programmers, we are system simulators. So we just want something that we can understand, not that it is the smartest way to do it. But here we will now store everything into matrices, and then we don't need either the figure or the hold on, we just need a plot sentence. Plot, and then you have time, and then the velocity, and then we have time versus position. So that should also be okay. And now he doesn't plot with circles or dots or anything, he will have continuous lines. What MATLAB doesn't like is operating with matrices and vectors inside a loop. Here, the first time n is going to be 1, then he has to construct a matrix or a vector v and x and t, and then increasing them by 1 for every loop. MATLAB is slow about that, he doesn't like it. So we should create space in memory before we start the loop. So here I should write something like this. V equals zeros. Zeros, and I want n max number, comma 1. If you forget the comma 1, then you will have a matrix n max by n max zeros. I can show you here. If you write zeros or 5, you see you get a 5 by 5 matrix, which is not what I want. I want to have zeros 5 comma 1. That's what I want, a vector. So that sentence will give me space in memory for all my v's, and the same goes with the x's. And now I can be smart, just write it like this, and the same with time, also need the same space in memory. That one is much faster than letting MATLAB increase these vectors one at a for each loop. So much better. Even faster would be to create this program without the for loop. That's possible actually, but we shouldn't overdo it. Okay. Any questions so far? That's okay. This is what you then have to do in exercise 1. Here, problem 2 with these rabbits and foxes. And the last point here, when we introduce hunters, then definitely you need some way to address 2-month-old information. Meaning you have to store the information during the simulation, or else it's not there. So I would recommend for that point, use a time step of 1 day. Remember, the time unit in this problem is 1 year, so that's 1/365. That's a delta t of 1 day. And then it's easy to address information that is 60 days old, 2 months old. So that's one way to work around that problem. Okay, that was a little side point. Now, instead of using first order Euler scheme, now I want to do it more accurately. I want to use MATLAB's ODE solvers. For those of you not too familiar with MATLAB, you can learn MATLAB by the documentation system. In the command window you write doc, and there you can get help for almost anything. So doc TEP4240 will provide us with very good information. How to use this function, and typically also interesting for us at the end here, see also. Then you have a lot of hints, tips, tricks, how to use this. And typically when you start using a program language, you don't know all the words. So you want to use a arcus sinus, for instance. But how do you write it? Well, you have no idea. Then you write doc sin, just for sinus. And then for sine, you will then go all the way to the bottom and see also. And there you will have a sinus, for instance. So the documentation system here is fairly okay. A lot of information here, typically, too much. So you scroll down till you find some examples. That's how you find it, what we really want to do. Now for our problem, it looked something like this. We had, what was it, v dot equal something, and then we had x dot was just v. That was our system. And these ODE solvers, they are designed to solve such problems directly. But to be able to do it, you have to use a function. Here you have an example, such a function, where you have a third order system. To the left here, you have the derivative, and 2 of them. And on the right, you will then have the right-hand side of the equations, here and here. So let's use this one for our problem. I just mark it here, make a copy, and then we go to our editor here. I need a separate M file. I need a function file to be able to use these ODE solvers. So I just punch in this function. What should we call him? Not rigid, we can call him actuator. Or I can just call him Funk actually. Funk. For this now I need 2 unknowns, 2 equations. The syntax for the function is sort of given. Here you invent a name. That's just internal for the function. That is what the function is going to return. What the function is going to return is these 2 values, just 2 numbers. The ODE solvers, they are going to use this function many times. And he's going to ask the function, what is the value for the 2 derivatives right now, given all the unknowns. And we only have two unknowns, velocity and the x. So here we have some x somewhere, and also we have some v as well. So you will be given these values, calculate these two. That's the only thing that your function has to return. And the name that he returns here is called dy. That's okay. Call it whatever you want. Now, I don't need the last sentence here, so I remove it. Also, here, I'm going to need a lot of unknowns. I need, well, not a lot, I need these two. But the function, the heading here, provides me with the time and then a vector called y. That vector, he will give me the numbers at the current time, what is x, what is v. And then it's very vital to have the correct number of the equations here. This is the first one, this is the second one, meaning the first number, that is, that's going to be the velocity. So I write it like this. Velocity equals y number 1. And then x equals y number 2. So I will always recommend doing it like that. You sort of translate from this generic vector y into your own symbols, into your own definitions. Then you don't have to use all these strange letters and stuff down here. You can remove it. Second, we need some constants. Let's see, where are all my constants? Well, I have a whole set of them. Here. Now all these has to be given somehow. So I just copy them. And I punch them inside here somewhere. Like that. That would be one way to do it. It's not nice, it's not elegant. Inside a function, you shouldn't list all your constants like that. They should be listed, the first statements in your main program. So here we transfer them by using a global sentence. So now we just write global and then the name of all our variables here. M. And it was B, A, K, well, the X0 I skip. So there I have now listed all the different parameters needed in my program. The same global sentence has to be specified in the main program as well. Here. Don't put that sentence all the way at the top before clear all. That's stupid. Then you define the global sentence and then clear all. He clears the memory and then he has forgotten all about it. So put it after the clear all sentence. That should be everything. And now inside my program I can copy this sentence directly here. There, everything should be okay except one thing. One thing we have to define here. PS equals 1. That one was not part of the global. But now you see fairly easy to do the programming here to recognize what the function actually do. He's calculating v dot, or dy1 is called here. Why not? What about the second one? Well, that was x derivative, or he's just equal v. And that's it. That's the function. That's the function ODE solvers need to find a solution. So let's try. We save this one. And he sort of demands name Funk. Well, fair enough. I overwrite it. It only exists already. So the second name here, that will be the name of the M file. And it will be the name that we now can use inside our program. In my program, now I have calculated the solution using the first order Euler scheme. To find out the S over a solution there, we do the following. You use square brackets, and inside there you will have two arrays, type and an array Y. See, that will be an array consisting of the solution at all the different times. The Y will be a matrix, the solution of all the unknowns at all the different times. You will see. TEP4240, that is the name of the solver, the built-in solver. He needs now to be informed what is the name of the function file that you are going to use. That's the first thing he needs. Second, he needs to know the time span, so that was from 0 to maximum time. And finally, he needs initial values. And again, the sequence, quite essential. The first value first. He needs the velocity first, and I call that one 0. Whoops, 0. And the next one was the position x, and that one was 0 as well. And that's it. That's all MATLAB needs. Call the solver using the function, the time span, and the initial values. I should have used a small v and a small x, but I have overwritten them during the simulation, so I just write 0, 0 here. Here, as I said, we will have a solution. So let's try if this one works first. I remove that one and write plot t, y. That's a quick and dirty way to do it. Y being a matrix, it should consist of two rows, one for the velocity, one for the position. Let's see if that's been correct. Something like this. Yeah. First one should be velocity. The velocity goes to 0. The blue one and the red one, that's the position. Yeah, he will level off at a negative position. So now we can compare. If we do it, we can continue here, comma, t, comma, v, and they can be, what was the velocity? Velocity was blue. Blue crosses, for instance. And then the position can be red crosses. So let's see how this one shows. Yeah, looks okay. Now I can go back and destroy or use a bad delta t, 10 times bigger. And then you see, okay, that's not correct. These UDES solvers, they are quite strong. UD45, he uses a 5th order accurate longitude to ensure 4th order accuracy. So he's very accurate. And for any problem, this is the one you will start with. That's sort of the workhorse for all these UD solvers, UD45. is very good. The first order Euler scheme you have to use with care, as you can see here. So you use smaller and smaller delta t and see, well, still not perfect. We need still smaller, down to say 2 or something. Now it's fairly correct, not entirely, but. So this first order Euler is very simple to program, but be careful, it's not necessarily accurate. So I will put out this script for you on the home page, so you will find it there. Any questions to this one? That's okay. So there you have the first recipe, how to use these UDE solvers. In the exercise 1, you are asked to solve a problem using different UDE solvers. And here you have a list, a whole bunch of them. But they are very easy to play around with. If you have program 1, you just change the name. So like TEP4240, that's, as I said, the workhorse, the one you will start with normally. But sometimes you will have a problem that might give you some strange results. You don't really believe it. It looks very strange. Problem there will typically be a stiff problem. Stiff problem. What's a stiff problem? Well, if you have time here and some signal or whatever, then you have a nice and smooth behavior, and all of a sudden, and then smooth again. Solve that one. That's a stiff problem. And of course, UDE solvers will have a hard time finding all the rapid changes here. It can be very steep indeed. So here TEP45 will have, oh, he will use forever. You can start him, but then he will just crash or stop or whatever. Then you can try with some of the others. So like 15S, that's for stiff problem, for instance. Of course, the problem that I have here is a linear equation system, not a problem at all. So he will give you a good answer regardless of the different UDE solvers you are playing around with. But when you try this equation, it looks very cute. It's a first order system, derivative equal to. But try to solve that one using, as it is said here, use the Euler method, use the different UDE solvers. You will run into problems. That equation is what I call infected. It's not possible to solve it. So regardless of method you choose here, it's going to explode. So the correct solution is rubbish. If you want to see how it looks, you have to sort of fix your axis correctly, or else you will just either have 10 to the power of 200. And then you will typically see the different solvers will try to get a solution, and then they will blow off either up or down. So you will have an image looking something like this in the end. Just try, play around with it. It looks very innocent, this problem, but it's a very nasty problem actually. So don't despair, don't start to cry if you can't solve it. It's not easy. The question is then, of course, why is it so difficult? That's a mathematical problem, so don't waste too much time on it unless you are a nerd. Okay? Yeah, then I don't think I will bother you with anything more today. Any questions? You will then continue tomorrow with chapter 2, source load. So, but now you have enough to jump into exercise 1 with the guidance on Friday. So we stop here.